Hey guys, I posted a webassign that should hopefully make your lives at least easy, is that it's all located in one spot. This video is hopefully you found it on the main page, but just a quick overview of helping you out with the webassign. Ultimately, I'm trying to introduce you guys to frictional forces. So you already have these notes actually in your notebook, but I wasn't sure if you had your notebook home with you. So I figured I would just do a quick video and add it on to the stuff for today. Yeah, so I mean, basically friction is it's called the coefficient of friction, and it's a ratio of the friction force that a block or a box or whatever it is can provide because of the type of surface it is with whatever it's sitting on. So surfaces come in pairs. Right, I can put a rubber tire on wet concrete, but I can also put it on dry concrete or on wood or on steel. And so every pair of surfaces has a set number called a coefficient of friction. And there's actually a difference between coefficient of kinetic friction and static friction. So that's what the video is going to kind of quickly discuss. I'm not trying to make this video last forever, so in a tablet mode, hopefully you can still hear everything just fine. Okay, so here's the basics. Right, everything that you have on the assignment deals with things moving along level surfaces, not on ramps. So that's important for you to understand that nothing's on a ramp. So if I have a box, and let's just say that this mass is 100 kilograms, then from what we've done so far, you know to draw the free body diagram, which has a gravitational force down, which is equal to 100 kilograms, the mass, times G on Earth is 9.8, which gives you 980 newtons. Okay, so now that you have that, you know that things that sit on surfaces aren't accelerating in the vertical direction, in the y direction. So you also know that there's a normal force here for this one that happens to be equal. This will not always be the case. I cannot specify, I can't point that out enough. This is not always the case. This is the case when it's not, when there are no other forces. So in an XY table, when we're organizing our work, we would write Fg and Fn, and then we would say together they equal the mass times the acceleration. In the y direction, nothing's happening. Doesn't move in the y direction at all. And so we would say that there's a net force of 0. And so this, then when we found Fg to be downward 980 newtons, that would leave Fn to have to make up the difference between negative 980 and 0, which has to be then positive 980 newtons. Okay, so we've done and talked about this. In the x direction, I can pull on this box. Now, if I pull only gently on the box, maybe with some applied force, or if I tied a rope, it would be a tension, right? If I pulled on this box or pushed on this box only gently with only 10 newtons of force, I could imagine that it doesn't budge, right? It's not enough to get it to budge and start moving. And that would be because I'm being matched in the backward direction. I'm trying to move the box to the right, but I'm being matched to the left by a static friction force of an equal amount. All right, and so that's not always the case, but it is the case if the box doesn't budge. Why? Well, because to the right I have F applied, to the left I have static friction, and as it turns out, when I set it equal to MA, if the box doesn't budge, A is 0, all of this becomes 0, and so then I know I was told I pushed on the box 10 newtons, so how much must static be? Well, it has to be to the left with negative 10 newtons, right? So kind of the same reasoning. But that's not always the case. So let's take a look. So the question that we're going to look at now is, well, what if I do push the box hard enough? Let's say the 10 newtons actually up above. Let's say that was just enough force to start it to budge, right? Like that was the exact moment when it budged. So 10 newtons was enough force. All right. In order to find out what that helps us with, it's called the coefficient of friction. write this symbol. It's really a Greek letter called mu. It looks kind of like a U, with like a little tail on it. Okay, so the coefficient of static friction, this is the equation we wrote in our notes, and we would just basically, it relates. It says the coefficient of static friction is equal to the maximum static frictional force over the normal force. Now, how do I know it was the maximum? Because the problem would say something like the box budges when 10 newtons of force is applied, right? Which means then for static friction was matching it all the way up until the moment it budged. Okay, so if this is the moment when it budges, then I can find the static coefficient of friction. I know how much friction, maximum static friction there was, 10. Anything bigger would have caused it to budge, right? So that means the static friction couldn't have matched it. Over the normal force, which is 980. Now, this is a very low coefficient of friction. But we get 0.01, all right? So 0.01 is the static coefficient of friction. Now, what's that helpful for? Well, it kind of isn't helpful after you get this. Usually the question is finding it, or you're given the static coefficient, right? So, I might say something like, here's a problem. You're trying to push your car, and it's on ice. So it will, it'll slide once you get it to budge, right? And you need to know how hard you need to push on this. So maybe you're not sure. Let's say you're not sure how hard to push to get it to budge. Let's say it's 1,000 kilogram car. And so then downward we have Fg is equal to 9,800 newtons. It's on a level road, 9,800 newtons normal force, right? I'm trying to make it look very similar to the last one. And let's say that we want to know how hard it would take to get it to budge. How hard do I need to push to get it to budge? Well, as I start to push even a little bit, friction pushes a little bit. If I push a little harder, friction pushes a little harder. And eventually I push hard enough where I get to this applied force, where I reach the maximum amount of static friction. And let's assume that the same coefficient of friction from earlier is the same for this car, right? So now I know the coefficient of friction is 0.01, and I can set it equal to Fs max, which I know is going to be the same as whatever I apply to get it in the forward direction. And I know the normal force, right? So in this case, we would be going the other way, and we'd multiply the two, and we get 9,800 newtons times 0.01. And we'd find that I have to push it with a force that matches the maximum static coefficient or static frictional force of 98 newtons for it to budge. Now, once it budges, that's a different type of friction. Once it budges, I have to deal with the kinetic coefficient of friction. And so in that case, I'm looking at Fk, and this is anytime something is sliding while it's sliding. So it can be going at constant velocity, or it can be going being accelerated, but it is moving and it is sliding, not a rolling tire. A rolling tire, believe it or not, is static friction, because the tire itself is only touching the ground at a moment. If I lock my brakes up and cause skid marks on the ground, then that's going to be kinetic friction, because the car slides along the ground. All right, and usually, like 99% of the time, the kinetic coefficient of friction, this guy, is smaller than the static coefficient. I'll explain that more in class. But if, let's say I get this car moving, right, and once I start it in motion, it only requires me to push it to keep it moving at a constant velocity. It only requires about 50 newtons of kinetic friction force of me pushing it forward. It's a very icy road. It's still the same car, 9,800 newtons, 9,800 newtons in normal force. And the question is, well, you know what? Hold on. Sorry about that. This is how much I push. So this is the applied force. But I know if I'm pushing it forward, then there must be a force pushing it backward if this whole thing is moving at constant velocity. So I'm pushing this along at constant velocity. So the problem would say something's sliding at constant velocity, or it would say it's accelerating and it would give you the acceleration. So in this case, all I know is constant velocity, which in the XY table, right, I know that there's Fg. I know it doesn't move in the Y direction, which tells me Fn is also 9,800 newtons, but in the upward direction. And then I know I apply a force of 50 newtons to keep it going at constant velocity. So constant velocity actually tells me that this side's 0 as well. It's not accelerating in the x direction. And with that information, then I know Fk, let me fix that, Fk has to be negative 50 newtons, right? And so this lets me wrap up the problem. If I want to find the kinetic coefficient of friction, I set it equal to the frictional force, which I just figured out is 50 newtons. And by the way, these are like absolute values. I don't care about negative signs because, I don't know if you noticed, but the units are going to be newtons over newtons, which means the coefficients have no unit at all. They're just a number, a ratio. So if I finish this off, I divide by the 9,800 newtons, and we find 50 over 9,800 gives me a smaller coefficient of friction for the kinetic coefficient. So that's our answer. That should be everything. I mean, the big change, the only other big thing is if I have a box and I pull on this upish at an angle, then from what we've already talked about in class, Fg is down, Fn is up, but Fn, in this case, cannot equal Fg. And you think about that and you look, it makes sense that when you go to fill in the XY table, in the Y direction I have Fg, I have Fn, but I also have F applied in the Y direction, meaning, let me see, do I have any tools here? I'm trying to look for another colored pen. I don't think I have one. Nope. Nope, there we go. So where's that F applied Y coming from? Because I pulled on that, or pushed on the box or whatever, slightly upward in the Y direction. So if I push on it, like pull it with a rope, it can be upward. Generally, if I'm pushing on it, it's going to be a downward push. So when I plug that F applied Y, it's going to be negative. Just like gravity is going to be negative here. If it was the car, it would be negative 9,800. Normal force would definitely not be positive 9,800 newtons. I have to do a little bit of trig to figure out, right? I have to do sine 30 times 100. The hypotenuse 100, and that will give me 50 newtons in the up direction. So I would have, 50 newtons there, and I know it still doesn't budge or something, right? And so you can see that there's no way normal force can equal 9,800 newtons. It has to equal 9,750 newtons. So it's actually a little bit less than it was earlier. Why? Because this applied force is upward, helping out the normal, so it doesn't have to equal gravity. It can be a little bit less than gravity, right? And then friction will always oppose, it's trying to oppose the direction of motion for this sliding friction. And if it's going at constant velocity, then you know F applied in the x direction is equal to the frictional force, right? So you got to do a little bit of trig there as well. Do cosine 30. All right, that's everything.